Mm. Yeah, so good morning, everyone, and welcome to day two. And we start off with Tim Hamilton, who's now become a good old friend. And we should all, first of all, the most important thing is it's midnight for Tim. He's at the University of Utah, and we're really grateful to him to staying up like this in the night to have this session. And we're looking forward to his session. Yeah, thanks.
All right. Thank you very much, Priya. As she said, I'm Tim Hamilton, and I'm glad to see what a large crowd there has been out for this event. And was sorry I wasn't able to come in person, but hopefully for another time I will be. I'm going to be starting us off today with a description of how to use integral field units and analyze their data in Python. So first, let me introduce you to what an integral field unit is. Let me get my PowerPoint going here. Now let's see here. If I share the screen and get it to the right one. Host disabled participant screen sharing. Let's see here. Priya, I think you're going to have to set me to a co-presenter or something like that again.
Okay. Yeah. Yeah, it's done.
Ready? Okay. There we go. All right, that's desktop 2. Is everybody able to see? Let's get rid of that there.
Yeah,
everybody
perfect.
able to see the full page? All right.
Yeah, perfect.
All right. So let's go off with what an integral field spectrograph, or simply integral field unit, is. Let's say that we've got in a traditional telescope with a camera, we would focus the image of a galaxy, such as this one here, and would send the light down directly onto a CCD detector or any other kind of modern digital detector. So we would get an image out of it. But let's say instead we focus the image onto this array of small lenses, not microscopic lenses, small lenses, each of which then separates one segment, basically one pixel of the image, takes it through an optical fiber, as you see here, and then rearranges those optical fibers into a kind of a pseudo slit, like the slit of a spectrograph, but made out of a row of optical fibers like this. Focuses that onto an optical grating, so a diffraction grating, which is then focused onto the normal imaging camera. In that case, we would be able to reconstruct the image in software, but for every pixel in the image, we would be able to have a full spectrum. Let me show you another method by which this can be done. You can take what's called a mirror slicer, or an image slicing mirror. And the idea here is if you focus the light down onto this kind of mirror, each of the segments of the mirror, each of the rows, is tilted at a slightly different angle. This will send its reflection off to a different part of the instrument, which will then separate these, sending them through a diffraction grating, and then their dispersed spectra are then sent on to the detector to be captured as far as the data. This, by the way, is one of the image slicers on the James Webb Space Telescope's integral field unit. So how the image slicing is done is if we have, let's see if my, going back there. All right. I don't know that I don't think my cursor shows up here, but anyway, at the top of the image, if we have an image of a galaxy, let's say that we have 6 slices on the mirror, then each one of those 6 slices of the image is dispersed perpendicular to the image direction. And so we get a spectrum of each of those slices. And then those are sent on to the detector. And then we can reconstruct the so-called data cube after the fact. This is a photograph of the MUSE instrument, MUSE instrument, integral field spectrograph at the European Southern Observatory. This is a massive one, what I think they're referring to as a second generation integral field unit. And this has both good wavelength coverage, very sharp wavelength coverage, good resolution, as well as good image resolution. When we think about the data product that is returned from an integral field spectrograph, we have to think in 3 dimensions now. Each pixel of the image has a spectrum. So if we look at it from the front of this data cube, we can see the image of, say, the galaxy that we're looking at. But if we look along the long dimension of it, the z-axis there, this is our wavelength axis. And we can either look at one pixel and take the complete spectrum of that part of the galaxy along all wavelengths, or we can select a single wavelength and look at the image of the galaxy at that wavelength, at a narrow band. And of course, we can do this for larger regions of the galaxy rather than a single pixel, and we can look at larger ranges of wavelength for the entire galaxy. As an example, I've taken some data from the MUSE imaging spectrograph, and here's a quasar. This is from their, I think, from their commissioning analysis of the MUSE integral field spectrograph. And what I've done here is I have taken a slice of the galaxy at the H alpha wavelength, which is, let me see here. Actually, I forget which one of these that I used. The H alpha might be the one that's in red here. The oxygen 3, let's see, red, green, blue. Okay, H alpha was red, oxygen 3 is the green, and the H beta would be the blue then, which is kind of overlapping with the H alpha. And so here you can see the different distributions of the different emission lines that are visible here. So that's one of the values of using an integral field spectrograph. You get this complete spectral information for the entire galaxy. You don't have to decide where you want to arrange a long slit in advance. Or, this is actually pretty interesting, as I was scanning through the data for this one, I looked at the oxygen 3 line at 5,008 angstroms. And as you scan through the wavelengths, I could see that the upper left section of the galaxy had that emission line peaking at a shorter wavelength than the lower right section of the galaxy did. That is, we're looking at the Doppler shift of the galaxy as it rotates. We're looking at how it blue shifts and red shifts the oxygen 3 line there. Here's another way of using these data. This is a radio map of the Milky Way up near the galactic pole. And in this case, we're looking at these large radio structures across the galaxy, but we're looking at a single wavelength of light, but we're looking at it as it is Doppler shifted due to the motion of these clouds. In fact, I'll show you very briefly here. Here, I'm going to have to share. Hang on, I need to go to my screen rather than to the, let's see, in show. Stop share. Let me go back to a new screen. Desktop 2. Okay. All right. Hopefully most of you may be familiar with the DS9 image displayer, which can handle these kinds of data. So I have loaded up a few integral field unit data cubes. Let me go to a single view here. This is the MUSE galaxy that we were just looking at. And let me just take a grayscale view of it here. Zoom in. All right. Now, the nice thing is, by the way, is everybody able to see this properly? Okay.
Yes, yes. All good.
Okay, good. All right. Now, if you look at the very bottom here, whenever you show a data cube, you have a screen that shows up, a window that shows up in DS9 that allows you to select the wavelength, which is shown here in this case in angstroms, whatever the data format is for the data cube. So let me move this back down, move it up a little higher here. You can see it well. As we go to short wavelengths, we've got that. As we go up to longer wavelengths, you can see it flickering as we go through emission and absorption lines. All right, so let's find, and at the end of the file, we wind up with some bad data there. But let me go find a bright emission line. This looks like a good one. I'm going to scan through these one by one. All right. So as I scan through these, just about 1 angstrom or 2 angstroms at a time, you see that we went down, we saw some absorption across the galaxy. Ooh, that was unusually bright. Okay, there's absorption. Now, look at the emission coming up at the upper left corner. And as we go to longer wavelengths, that emission moves down to the lower right. So we're actually seeing how the spectrum is Doppler shifted, bluer on the upper left, redder on the lower right then. Going backwards a little bit there to bluer wavelengths and going back to redder wavelengths here. Okay. Now, so that shows you what we can do with these. Another one, just to show that here's that data cube of the Milky Way with the radio. And if we scan through, in this case, it's not put in terms of wavelength or frequency. It's put in terms of radial velocity relative to the Earth. So we have basically bad data for a lot of ranges here. They shouldn't have kept this in the data cube. I don't know why that's set up that way. Okay. So here we have, I don't know what the units are on this. Oh, it's negative. So that should be moving towards us if the redshift is negative. And as I scan through it, we're looking at all these complex structures. You can see probably magnetic field shapes there. Okay. Now, here's the interesting part. Look at this cloud here. And as we go to more positive radial velocities, we can see the structure of it out like that. So we're looking at the structure, the three-dimensional structure of its motion here. Once again, on like that there. Okay. All right, let me go on back to sharing the PowerPoint. Okay, and to the PowerPoint. All right. Hopefully that's showing it properly. All right, so what I'm going to do here is take you through the analysis steps, just a very basic one, in order to show how to read in data from an integral field unit data cube, display slices of it, say at H alpha and oxygen 3 wavelengths, take a ratio of those two and save the result as a new file. I'm taking this, actually, I'm adapting it from a tutorial that's already available on the web. You can see the link down at the bottom, and that will be available in the PowerPoint, which I'm going to send on to Priya after my talk. So you can walk through this here. I've added on some things to it, but the main thing is that their tutorial, while it will take you through the steps, does not explain very much. And there are a lot of things that are confusing about this. So we're going to go through this here. First of all, let's read in the data cube. Now, the first line of this here, now you notice that I'm going, actually I should start here. These are just for those who are new to Python. What we're doing is we're importing various packages that will allow us more functions that are defined to give us more ease of some commands that we can to use for this here. All right, the most important of these right now are NumPy, or numerical Python, and we're going to abbreviate it with NP. We're going to use matplotlib, which I understand that Priya will be speaking on this afternoon. I won't try to explain much about it then, but once she's gone through it with you, you'll have a better understanding of what we'll do with this. And it's just, we're going to be using it to display the image. There is the fantastic and reasonably new package called AstroPy, which I think all of you should get to be familiar with. And we have both the World Coordinate System package in that, WCS, that allows us to handle the orientation, the scale, the direction, positions of these images, right ascension, declination, and so on. And we also need, from their input-output part, to work with the FITS file format. If you're not familiar with that, it's Flexible Image Transport System, but really it's just the standard astronomy file format. It allows us to store data, to store images, tables, arrays, and we also have header information like metadata, which is going to be very useful for us. Okay, I'm going to go through these kind of a line at a time. The first thing here, we're going to use the FITS. This is a bit of syntax. If we have imported the FITS package from AstroPy, then in order to call a function within that package, we have to start off with the name of the package, FITS, and we put a dot and then the name of the command, the name of the function there. So this is that kind of syntax that we're going to be using. We're going to be opening this file name here. And if you go to, let's see, if you go to the link that I gave you on the first page, you'll be able to, they give you a command to download that file on that. So you can get that yourself as well. And that's just, it's a file name there. And we're going to assign all the facts about that file to this variable name cube. So cube will now represent, this is, I guess this is really an aspect of an object-oriented programming language, which it took me a little while to wrap my head around exactly how to use that in numerical analysis. But once you get the hang of a few things like opening files, you'll find that this is very useful. Just so that you know, the file format, the file name format for these, this is called a log cube file. It's one of the many kinds of data products that the Sloan Digital Sky Survey puts out. And we're using it from their, going back up, we're using it from their integral field spectrograph called MANGA, M-A-N-G-A, which is a fiber optic fed integral field spectrograph, which has very low quality imaging, but very high quality spectroscopy. And so we're going to be looking at the spectra, but we're not going to worry too much about the image parts of it, which is going to be very crude. All right, so now we've assigned that file to cube. All right, let's see, and that's just what I explained there. If you're not in the same file, if you're not in the same directory, then what you need to do is to include the path to the file name in the open command. By the way, I think I heard a comment maybe come up on the chat, but I don't see the chat on here since I'm on this. Okay, the next step. Oh, was there a question or something that came up, Priya?
No, we can hear.
Okay, good. All right, the next step, we're going to take from the cube variable, which now has the whole file assigned to that. FITS files can have several different extensions. Essentially, you can have many different images all in the same file. Some of these extensions, as they're called, could be images, others could be data tables and things like that there. But in most cases for these, we're dealing with things that are arrays that match up pixel by pixel to the image, and it may be something like the error on each pixel flux. It could be the exposure time, or it could be flagged data where we have bad pixels and things marked. In this case, one of the extensions is called flux. That's going to be our image data. And in order to pull out the data from that extension, we use what's called a method. A method is the object-oriented equivalent of a function. But while a function would say something like data and then parentheses, you put your argument in parentheses, cube flux, like that, close parentheses. A method is tacked on to the end of the name of the variable. So it works sort of backwards in the notation. So if we've got the data cube called cube, and we're looking at the extension in it called flux, we just put dot data, and that will give us access to the data within that extension. The next thing we're going to do is we're going to transpose this. The thing is that in, let me see here, my next one. So the FITS files from the manga instrument are stored in the order of the X coordinate, Y coordinate, and then the wavelength lambda. So columns, then rows, then wavelength. However, the Python coordinate system is reversed from these. It always has row, then column, or basically Y, then X. So the top left pixel in an array has the coordinate 0, 0. Your origin is not in the lower left. We're working with images. We want the bottom right to be, I said bottom right, that should be bottom left. Should be 0, 0. So make sure you know that. Okay. So what we're going to do, the first thing is we want to switch the order of the axes around. Python also starts counting in arrays and lists with 0 indexing. That means the first element of an array is indexed 0. If you're used to working with other languages like IDL and Fortran, you're used to indexing starting with a number 1. So we're going to, the transpose in the NumPy, we're calling it NP, we've abbreviated it. The NumPy transpose function allows us to switch the axes around. So the last axis, the number 2, which is the third one, is the, let's see here, wavelength. Number 1 is X and number 0 is Y. Yes, I believe I've got that right. X, Y, lambda. Oh, no, we're going to, sorry. It read it in lambda, Y, X, and we're going to switch this around to make it X, Y, lambda. There we go. It's always confusing the way it reads that in. And I've given you a link so you can see how the data model is set up for the manga images, these are good ones to start with. Next, we're going to do exactly the same thing for another extension within the file, and that is the inverse variance extension. So for every pixel in the image, in many other observatories, you'll have the error in that flux reading. In the case of the manga instrument, and I think all of the Sloan Digital Skies survey data files, they use the inverse variance, 1 over sigma. And so for that, the advantage of using inverse variance is that a bad value, which has essentially infinite error, simply has inverse variance as 0. So that's handy to go by then.
Tim, we have
I see the question there. So is there a built-in function to convert images from any other format into FITS format? They are not built-in functions. However, there are software packages that will allow you to convert between these. What may be, or at least they'll allow you to read in the data arrays from other kinds of image file formats. For any kind of astronomical work, you need to have what's called a lossless file container. You don't want to work from a JPEG image, for example, because the compression method for JPEG it rounds off data in order to compress it, and so you lose some information in the process. While in the FITS format, there is no loss of data. However, there are things like the TIFF and the PNG, I forget what it stands for, file formats that are also lossless, and there are Python packages that will let you read in those. Right off the top of my head, I don't know which packages those would be. And then you'd be able to take an array from that after you read it in and treat it the same way you can right here. By the way, a great thing about Python is that it's so popular now, and it is, I would guess, the most popular language for data analysis in astronomy. That if you want to do anything in Python and you wonder if somebody's already written a package to do it, Google that. Python, is there a Python package to do whatever? And more than likely somebody has written that and it will come right up. You'll get a whole lot of results from the Stack Exchange and Stack Overflow discussion forums. That's where I've learned a whole lot of what I do here. Okay, so we're going to do the same thing with this one. We'll reverse the axes, and we're not going to use this inverse variance extension in what I'm showing you this morning, but it's there if you want to take a more careful look at the data and select your best data. Those that have good quality are going to have a high value of the inverse variance. Those that are close to zero is going to be bad data. Okay. Now, then we've also got the same thing with a mask array. This is a great feature of all kinds of professional observatories where they tell you in other observatories, it may be called a data quality array. And what it is for every pixel in the image, it will tell you whether the data from that pixel are good. Usually that means no flags are set, or whether there are certain bad indications set, or whether it may tell you other information about it. In this case, it is usually these are done as bit flags. So if you have a binary number in that for every pixel, the value of each individual bit is a different flag. So the first bit may be telling you whether it's the pixel has got damage to it, and the second one might tell you whether there is there was cosmic ray damage or things, and so you're going so on like that. By the way, you'll see I'm referring to spaxels here rather than pixels. Sorry, I should have made that clear. The spaxel is a spatial pixel because, of course, we have two spatial dimensions and one wavelength dimension for the data cube. So the spaxel is an image pixel, a spatial pixel. Okay, so in this case, for the Manga instrument, I've given you a link to their bit masks. Any spaxel that has the 10th bit set equal to 1 is a bad spaxel, and you shouldn't use it in the analysis. Now, the 10th bit has a value of 2 to the 10th power. I've done the double asterisk exponent notation here. 2 to the 10th power, which is equal to 1024. And later on, I'm going to show you how we can check that bit. So just as an example, if you want to set, let's say you had some other mask array, and the value for this particular pixel was 6. Well, you write it out in binary. That's 110. That's from the right to the left, going backwards. We've got the 0 place. That's 2 to the 0th power is 0. 2 to the first power is 1. 2 to the second power is 4. So we've got those values there. Oh, you know what? I'm sorry, I must have done that so hastily the other day. 2 to the 0th power is, of course, 1. It would not make any sense to have them. All right, 2 to the 0th power is 1, but you knew that. All right, so the first bit number 0, the right-hand one, is not set because it's equal to 0. Bit number 1, the middle one there, is set, and bit number 2 is also set. Okay, so that's how you could look at the flags. All right, the final thing for reading in here is that we're going to look at not the final one, we're going to save the wavelength labels. Now, the data cube, all the file shows itself is that we've just got this three-dimensional array, 3-axis array. 2 axes are pixel coordinates, and the third axis is wavelength coordinates. But we don't know what those wavelengths are. What is the wavelength that corresponds to the third element of the wavelength axis, for example? We don't know by itself. Luckily, we have an extension to the file that has the wavelengths listed. And so we use cube, we go to the wavelength extension, and the .data method reads in the wavelength values for each of those coordinates, and we save that as the variable wave, which is going to be a one-dimensional array. Okay, we don't have to transpose this one because it's not an image array. It doesn't have two dimensions. It only has one dimension. Okay, next, we want to pull out header information. Again, if you're not familiar with a FITS file, the header is equivalent to metadata. It tells you when the picture was taken, what the observatory was, the target name, and importantly, coordinates on the sky, which we're going to be using. Okay, so we can take the header from the flux extension. Each of the extensions can have its own separate header for whatever information is important about that extension. Furthermore, there's what's called a global header or primary header, which can tell you more about the entire data set. And that's usually a very short one. Okay, now, if you're following along on this, you can print out the shape of each of these arrays just to check what their dimensions are. The print statement, this is using the Python 3 version. Python 2, many of you may already be familiar with. The print command was a statement and it didn't use parentheses. There was no argument to it. In Python 3, they've changed it to where print is now a function and it requires parentheses there. So in this case, what I'm doing is I'm printing out the flux array, but not the whole array. There's what's called the shape method, or the shape attribute belonging to the flux array. Every array has a shape. And that shape is the dimensions of the X, Y, and Z axes. Or in this case, now I've got it X, Y, and the wavelength axes. So we've got 74 pixels wide, 74 pixels tall, and 4,563 wavelength measurements we have for each one of those. And when we print the shape of the wavelength array, the bottom one there, all we get is the single dimension. You might wonder, why is there a comma following that? Well, I wondered that too. This is a quirk of Python. When we have a one-dimensional array, the syntax allows in ways that are still a bit beyond me. That comma simply allows for, if you wanted to add more dimensions on, it would tack them on at the end there. That's my best way of explaining it, and probably not exactly correct. Anyway, it's still a one-dimensional array. Okay, now what we're going to do in the first case is we're going to plot the spectrum for the central pixel of this array. We need to find the central pixel in X coordinates and in Y coordinates. And honestly, since we know it's 74 by 74 pixels, we could just pick out, what that'd be, 37 or 38. But we can find it automatically. Maybe we have a very large image we wanted to find that. The X center pixel would be using the NumPy function integer. This will convert whatever you put into it into an integer. We pull out from the flux header information, we pull out the keyword center pixel 1. And that is a standard FITS keyword, and the value is the central pixel on axis number 1, whatever that axis is. Now, we're going to subtract 1 from it because in Python, we start counting with 0. So we've got to change that over. We do the same thing for Y, center pixel 2, Y-axis. Now we're going to use the matplotlib pyplot, which we've abbreviated PLT, and we're going to pull out the plot function. Again, Priya will be explaining to you about matplotlib later today. Basically, it will plot you a two-dimensional graph, just a line graph. Wave, we have our X coordinate, our horizontal value, and our vertical value. So the horizontal value are the wavelengths. That's on our horizontal axis. The vertical axis, we're going to take the flux. The brackets give us the X and Y coordinates. We put in the X and Y coordinates in that flux array. We pulled out the center ones there. So that gives us simply a single one-dimensional array of what's left. The flux at every wavelength for that central pixel. plt.x label, plt.y label allow us to give X and Y coordinate axis labels. Wavelength in angstroms, I printed out there, just I typed it in. For the y-axis, we're going to pull in information from the file, which it lists what the units are of the flux units. And from the flux header, we look up Bunit. Well, Bunit stands for brightness unit. And again, that's a very standard FITS file keyword. Okay, I went through all of that already. Oh, and when we're done, we write out show, and the show command, the show function, which takes no arguments, simply displays the plot once we've already defined what the rest of the plot's properties are. And here's what we get. The little numbers in blue on the left, there was a display error when I was copying and pasting this. Okay, so there it is. We've got wavelength in angstroms along the bottom, and we've got the brightness ergs per second per centimeter squared per angstrom per spaxel, for one spaxel, along the vertical axis. So we can see some bright emission lines. Now, the nice thing is that we get we have tools in the displayed window that comes up. There'll be a separate window in Python, and we can use those tools to do things like zooming in closer. So here I zoomed in on some of the emission lines. You can see the clusters of them right there. Okay. Now, what if we want any old pixel and all we know is the right ascension and declination? Well, we have some tools in Python and AstroPy to convert between world coordinates, right ascension declination, to pixel coordinates. And what it does is it uses this so-called world coordinate system that's in the FITS file in the header. So we're going to take from the AstroPy world coordinate system package. From that, we take the function capital world coordinate system. You'll see this kind of lowercase WCS dot capital WCS all the time in Python. And we're going to plug into it the flux header, which we've already pulled out. We're going to assign the world coordinate system part of the header to the array cube WCS, world coordinate system for data cube. All right, now let's give right ascension declination in decimal degrees here. And then we're going to plug those into this other function, world coordinate system underscore world to pix. It converts world coordinates to pixel coordinates. I'm not going to go too deeply into it, especially given the time, but you'll have to look up the instructions for that one. But it takes right ascension, declination, and right now we don't need any other. We're just going to put one on that. I don't even remember exactly what that third item stands for. We've got to put it in a double bracket. This is because you've got other kinds of data structures called tuples in Python. And sometimes you've got to have an array, and the whole array is the first element of another array. In this case, that's the only thing in there. Okay. Now, this world to pix gives us a set, it gives us the output array we want, and then other stuff that we don't want. And so we can simply index that with a 0. We'll take the first element that comes out, which is going to be the array we want. And we can assign the 3 numbers that come out. The first one is the x coordinate that of corresponding to the right ascension declination. The second is the y coordinate, and the third is this underscore. Now I wouldn't have done it this way, but I'm copying out what they did in that tutorial. This is a double underscore, underscore, underscore. That's a variable, that is a valid variable name in Python, which looks very weird. You can use it to prefix other variable names. And I believe the usual approach is that it makes them local variables and not global. And that avoids some complications when you're doing much more complex programming. Most of us don't ever need to bother with it. In this case, they simply do it so that because they're just going to throw away that third value. And so they just assign it to underscore. They don't even look at it again. All right. Now we're going to give the correct spaxel coordinate we got to go the innermost part of the argument to the outermost. We take that X coordinate, we round it to the nearest integer value, we convert it to an integer variable format. Okay, we don't just round it off and leave it as rounding leaves it as a floating point number. It's still got decimal .00000, but we want to force it to be an integer data type because that's what we're going to need to read in. And then we subtract 1 because we're counting starting with 0. Okay, now we want to plot the H alpha image. That's our next bit that we're going to try. So there are some bad data points on this, and we're going to throw those away. We're going to mask them and not use them. So remember when I said that we could take the mask array and we could use it wherever we find a bad data point, and we could clear it off by checking to see if bit number 10 is set. What we do is we're going to make a new array called do not use. It's going to be the ampersand symbol is a bitwise AND test. So if we take mask, which is a whole array, we do an AND with 2 to the 10th power, that's 1024, bit number 10. Every pixel for which that particular bit is set will, the AND will give it a 1 value that comes out. We'll just get that. Now, you could have said equals 0, meaning testing if it's, sorry, equals 1, testing if that bit is equal to 1. For whatever reason, maybe because maybe they worried that they had programmed it wrong and maybe it would come out to be equal to 2 or something, which it can't. They said not equal to 0, a more complicated way of doing the same thing. So they test to make sure that that bit is not 0. If it's not 0, then it's going to be 1 and it goes into this do not use. Okay, so the mask is going to be that array there. Let's go on to the next bit here. I've already explained that part. Now, here's a neat thing. NumPy, numerical Python, has a new data type, a new kind of an array called a masked array. It has 2 parts, the data part of the array, and then corresponding element by element, you have the mask array. And you can set it this way. You create this masked array called flux_m, that's masked flux. You can call it X, anything you want. NumPy.ma, masked array. And in parentheses, you put the data array first, that's flux, comma, you set the mask equal to, that's a label for it, whatever you want the mask to be, do not use in this case. Okay. Oh, and I should note as well that when you check that the values are not equal to 0 there, you're going to get either a true or a false. Now, that also means true is 1, false is 0. You could set it 1 and 0, but this is a logical test and you get true and false there. Okay. Let's see here. If you want, by the way, when you want to get out the masked array values, let's say down at the bottom, I just call a masked array and call it blah. Okay, masked array.array. And I put in a 1-dimensional array with values 1, 2, 3 for the data, and the mask values are 0, 1, 0. Okay, so the first value, this one here, number 1, is not masked. The second value, which the mask is equal to 1, so it is masked, meaning it's bad. And the third value is not masked, so it's good. If we want to get the data out, we do blah.data, up pops array 1, 2, 3. If we want to get the mask parts, we do blah.mask, out comes false, true, false. Okay, so let's plot the image. Well, we want to find the H alpha emission line. Now, we have to look up the redshift of this galaxy, or we can use the spectrum we plotted earlier to find the redshift. Now we're going to find the index values of the wavelengths that correspond to H alpha. So we use a nice function called where. The where function will, you put an array into, you put an array and a condition into it. and it will tell you the index values of every element of that array where the condition is true. In this case, we're feeding in the wave, that's the array of wavelengths, and we are converting them into the rest frame. So we take the wavelength divided by 1 plus redshift, 1 plus c, and we're testing if it is both greater than 6,550 angstroms and it is less than 6,680. Basically, that means it's within 15 angstroms of the center of the H alpha line at rest wavelength. Okay, now the where value, so wave is remember that's an array, there and there. And then where returns that one-dimensional array of all the indices of the wavelengths where that's true. But of course, it does this with a tuple, and we only want the first element, so we have to index that with a 0. If you, by the way, just printed it out without the 0, you'd see it would be everything you want, comma at the end or something like that. All right. Now, if we want to make an image, an array that's just the flux contained within that range of wavelengths, that narrow range there, we use this format. We're going to use the, let's see here, what do we call that? Flux M, that's the array of flux data, but it's got a mask. Okay. The first element, you see a colon there. That means you use colons when you're separating the minimum and maximum values of the range of indices in an array. If you just put colon, that means everything from minimum to maximum. So for the X coordinate, we use all of them. For the Y coordinate, again, we use all of them. So that means we're taking the entire image. But which wavelengths do we use? That third axis, that third index, we're only using those indices that passed the test, that are within that range there. So we take the index of the wave, the proper wavelengths, and we put that in for the third axis. The next thing we're going to do is even cleverer. Out of all of those, we're going to add up all of the flux values for a given spaxel, remember a spatial pixel, all the flux values along the last axis, axis number 2, 0, 1, 2, which is the wavelength axis. So for a given coordinate on the sky, we will add up the flux for that position at all wavelengths within the range that we've selected. Okay, and that gives us an image summed up, integrated really over the range of wavelengths for H alpha. I really do like some of these techniques you can use here. How to remove the point source objects in a FITS file. Oh boy, there's a whole art to doing that. Vignesh just put in a question about that. Removing the point source objects in a FITS file. If you're using in Python, I don't know for sure, but probably there is now a version of, let me think, what is it called? There's an old IRAF package called, let's see, QFITS, which allowed you to build up a stellar point spread function. But really, these are tricky techniques in a lot of ways. I've written whole software called StarFit, which will allow you to do that. It will allow you to model it, then you have to subtract it yourself. You can look up StarFit, and I'm working on a version which is my old version. It runs in Python 2, and it uses IDL and IRAF. The new version, I'm trying to make only Python and Python 3, but I'm not finished with it yet. That's going to take me another year probably. So anyway, yeah, unfortunately, there's not a simple answer for that. But take a look at something FOT. There's QFOT, and then there's DAOPHOT, DAOPHOT in Python, in IRAF, but they may have a version of it in Python. That might be your first thing to go to. Okay, now, just before we can plot it, we need to put on the coordinates here. And so we can display it with north up and east to the left. First of all, we want to transpose, because remember, we're going to be displaying it X and Y. Python is used to going Y, then X. So we can just use not a method, an attribute here. I guess, no, it is a method. For any array, we can put a dot capital T, and that gives us the transpose of that array. All right, now we're going to convert from the X and Y coordinates to world coordinates in arc seconds relative to the center of the image. I'm not going to go into great detail on this here. This is more world coordinate system conversions and not so much a Python thing. Plus, it's confusing to me as well. But I put a little bit of a note here at the bottom with a link to where I got this paragraph from. The world coordinate system in a FITS file uses, the standard uses a rotation matrix. So you've got your deltas of your kind of your scale and the rotation for the X and the Y coordinates, or coordinate 1 and coordinate 2, axis 1, axis 2. In the old days, they had used C delta 1. I don't know what C stands for, coordinate maybe. Delta 1 and C delta 2, those gave you the scale, values per pixel. And then C rotation 2 would give you the rotation of those axes from your world coordinate system in degrees. Okay. In FITS, we've got more sophisticated. We might be able to stretch it and squeeze it and then rotate it and so on like that there. So we have these 4 elements of a coordinate rotation matrix. So remember, C delta 1, C delta 2. We've got the cross terms, the common terms, and so on. This gives us the angle, let's see, the scale and the angle like that there. Anyway, you'll have these 4 numbers that are in the FITS file, and you can use what I've shown here to pull that out. The only other thing I'll mention about this is the extent is simply going to tell the display function how far out, what the scale is on the screen that you're putting it out there, and we're just pulling that in automatically. All right, but here's where the magic really happens. The PyPlot function imShow, that's image show. The first thing it takes in is the array that's going to be your image. If you go back a couple of frames, one frame, the array, the image that we're using, and again, we can call this anything we want, is the H alpha array that we just summed up. Now we've transposed the X and Y coordinates. The extent, okay, that's a keyword here. Well, we've got a variable called extent, or an array called extent, which will give us the X and Y limits for this basically. CMap is a keyword that means the color map. Here, the ones that they chose, color map, and it's yellow, green, blue. It's not my favorite set of colors, but it works. Vmin and Vmax gives you the minimum and maximum values that you will display. The origin is going to be in the lower part, and we're not going to do any interpolation. Okay, we're able to display a color bar on the right-hand side that'll go along with a legend, and it will show us what colors correspond to what image values. And we can pull the label for that in from the brightness unit keyword in the FITS file. We can label the X and Y axes in arc seconds, and now we put plot.show, and up it comes, and here's what it looks like. Okay, so we've got this on the sky. We can see a galaxy, maybe with a second, or maybe a small galaxy that it's swallowing up there. We can make out some tidal tails, maybe on the upper right. The image quality, like I said, is very blocky. It doesn't have that many fibers, but they can do sampling on the sky to make it a bit better and a bit smoother. All right, so that's it. Dark values are low, bright pixels are brighter. Okay, but let's go a little bit farther. Let's take a look at another emission line. This was H alpha. Let's take a look at the oxygen 3 5008 angstrom line. Now here, since we've already done all of the hard work already, we can do the second part of it very easily. I'm going to pull out the indices of a second set of wavelengths. I'm going to use the where function to give me the indices where the wavelength is no more than 15 angstroms from the oxygen 3 line at that redshift. So wavelength divided by 1 plus z gets us to rest wavelength. And I just went from 5008 plus and minus 15 angstroms there. Again, we've got to take the first element. I'll call the O3 array to be the flux from this a masked flux array, all the X values, all the Y values, but only the wavelength values that passed this test. And then we're going to sum up the flux along every wavelength within that range for each pixel. Okay, now we're going to do the same plotting command there to show it. The values here, you have to do the same range of values, same color bar, same everything else, so on, and it looks basically the same. Let's try one more thing, though. I'm not going to show you the O3 because it looks identical here. But let me show you one other thing that we can do. Now that you have an array for H alpha and an array for O3, the great thing about what you can do with these integral field units is you've got it for every pixel. So what if we were to take the ratio of H alpha to O3? Oh, you know what? I mislabeled that. It's O3 to H alpha here. I started doing it H alpha to O3, then I realized to match up certain useful things, we want to go the other way. So I'm going to call this image ratio number 2, because I did another one earlier, where I take that second image, that's O3, and divide it by the first one, which is H alpha. And it does this when you have arrays and you divide one by the other, it does it element by element. So it knows the 0, 0 coordinate, it's going to divide that by the 0, 0 coordinate of the next one. And then I display it here the same way. And what do we get? Well, I'm going to pull that up. Let's see, I've got to stop sharing, and I'm going to share the screen, show the display. Desktop number 2. Okay. Let's go to the next one here. Here we go. This is the ratio of O3 to H alpha. You can see in the bright areas in the center of the galaxy and on this little companion galaxy that the O3, the oxygen emission, is very weak compared to the H alpha. In these outer areas, and maybe in the tidal tail up here to the right, it's actually a higher fraction. But still, it's less than, it's always weaker than the H alpha emission. Now, a caveat here, despite the fact that this looks like, you've got real patterns going on. Maybe we've got bright O3 down at the bottom and up here, and we've got this bright area here. It may be that we didn't really analyze it properly. For example, okay, what you've got to do is you've got to subtract the continuum properly in this case. And I didn't really do that carefully. In fact, I didn't subtract the continuum at all. You could go back and take a look at the spectrum, and then you could figure out the continuum levels by doing a fit to that there. That would be a proper way to do it. But keep in mind, let's say you're looking at an active galaxy like a quasar. You may have one shape of the continuum, let's say a power law, for the active nucleus. And then you have a very different looking continuum when you have a star forming region or nebulas. So you'd have to do it really well. If you have different emission sources, you would want to fit the continuum separately for every pixel, a spaxel, or maybe for every small group of spaxels across the image. That would do it properly then. But I'll leave that as an exercise to the reader. All right. Another thing here, let's save this file as a new FITS image, this ratio of the O3 to H alpha. And I'm called in this case just testfits.fits. I could have come up with a cleverer name to it. What you do is you use in AstroPy, there's the FITS package. You use the write to command function. The first thing you put in the argument is the file name you want, and you can include a path in there, all in quotes, comma, then you put the data. Now, here's the thing. I made a mistake when I first tried this, and in fact, it was earlier tonight, where I tried, all right, image ratio 2, and should save it. And it complained. It gave me a very long list of complaints that why it did not like that. It took me a while to go through it. I finally realized that was a masked array. It has 2 separate arrays within it. You can't save that as a FITS file. You have to take a single array. So how do we get the data out of that? Here's our masked array, image ratio 2, dot data. And that, whenever you see that together, that is that array now. And then finally, we want to have a header to put onto the FITS file. I did, as a quick and dirty approach, I simply used the flux header that we had used, that we'd taken out when we pulled the data in from that from the file to begin with. However, be careful, because this does not put on the global header, which has a little bit of extra information that you might want. So take a look as you go on through the workshop this week and see about how you put on more specific headers then. Okay, and that is it for mine. So I'll leave it to Priya about questions then.
Yeah.
And I'll leave it on sharing on mine until we're done with the questions for me, in case I need to pull something up here.
So thanks so much, Tim. That was a lovely, lovely introduction to integral field. And yeah, there's one on the chat: how to remove point sources in a FITS file.
Okay. So in the point sources, if you're just looking with a standard image in your FITS file, then there are ways. I mentioned before the DAO, let me think here, DAOPHOT, DAOPHOT. I'm putting that in the chat. Is one package. It's built into IRAF, at least with the Space Telescope packages there. And then there are standalone versions. I'm assuming somebody has created a Python version of it, but I have not used that. IRAF is still available, even though it is not officially supported anymore. It's now volunteer supported, but you can still install it. And in fact, I'm going to need to on my new computer. There's also the StarFit package, which set of software, which I have written, and I'm in the process of updating from Python 2 to Python 3, and I'm hopefully going to be able to get rid of all the dependence on IRAF and IDL. So everything will be native Python on it, but that's going to take me a considerable more amount of time. I was hoping to have that done this past summer, but I'm still working on it. But there are other quick and dirty methods. You could just take fit a Gaussian to your point source, if it's roughly Gaussian in shape, and then subtract that away. For that, you would really have to write your own routine. It wouldn't take you too terribly long, but you could do that completely within Python. Now, if you are using an IFU, for example, like I was showing you here, it's going to be more difficult because each of your point sources may have a different spectrum to them. They may look the same shape at one wavelength, but if you look at different wavelengths, well, for example, if it is a very red spectrum, then you're going to have less light in the blue and more light in the red. That means that the red wavelengths, it's going to be wider. Diffraction pattern is going to be wider at longer wavelengths. And at blue wavelengths, it's going to be narrower. So the combination of those, it changes the shape. To do that, then, again, you simply have to do it for each wavelength in turn. And you may just have to write your own software for it, or do repeated analyses at each of the different wavelengths there.
But what about source extractor? Source extractor can classify, right? If you basically what they're saying, if you want to remove your point sources, and if you run source extractor, it will classify it, and you can, remove your point sources, keep your extended ones, right?
Oh, and also I think that what's the source extractor software is also able to separate extended sources from point sources.
That's it. Okay, there's another one. Sorry. Go on.
Next question: how do we do integral field units with James Webb data of distant sources? Okay, well, I am hoping to use the integral field units on the James Webb sometime soon. I haven't gotten time for it yet. I haven't gotten time on it yet. For this, it's really not any different from any other in the analysis, whether it's a distant source or nearby. The only difference there is that it's going to be fainter, and so you're going to have a larger amount of noise. But I might have to ask you then, what kind of analysis are you wanting to do with? Simply looking to see what you've got, or are you wanting to fit particular things, or do you want to take out a given one wavelength, for example, and analyze that? Tell me what you have in mind there.
Hello, good morning, sir. Sir,
Good morning.
yeah, sir, actually, I was planning to study the distance galaxies, maybe the spectrum. So, how to go about it? How to reduce the noise? Yeah,
So you want to pull out the
thank you.
spectrum of a distant galaxy, is that correct?
Yes, sir.
Okay, so for doing that, in fact, I'll show you a quick approach with, let's see, I'm still sharing my screen? Good. If I pull up, let's go to this one here. In fact, this is the galaxy that I was just showing you. I'm going to color it black and white or grayscale, just so that it's easier to interpret right now. Okay. Now, as we scan through at different wavelengths, you can see emission lines, things like that pop up. Now, to get a quick look to begin with, before you start the analysis, just so that you know what it is that you've got, if you use the DS9 image viewer and you create a region, are you familiar with using DS9?
Yes, sir. I am using DS9.
Okay, so let's create a region here. I'll make it fairly large. All right. Now, because this is an integral field unit set of data, I double click on it like this. Bring that up there. And I'm going to hit analysis. And let's see here, wait. Hang on a second. No, there we go. You've got to select the region window here. And analysis statistics. Oh, that's not statistics. That's not what I wanted. Analysis plot 3D. That's what I wanted. Okay, came up on my screen. There we go. All right, so now we have the spectrum right here. Now, this will give you a quick look, but you can't do a whole lot of analysis with it right here. You can zoom in. I thought you could zoom in. Anyway, it gives you and you can even download this. You can save the data right there. But this will at least show you what you're looking at. Now, the reason I'm showing you this here is if we go, let's put it down at the bottom, make this a bit smaller. All right. As I move this around, look at how the spectrum changes. As I go to this other galaxy here, you see the spectrum is already showing me differences between the two galaxies. You can see the absorption lines at the blue end over here, which we don't see in this active nucleus. I think that's an active galaxy there. Out here in the arms, we see strong absorption and not very much emission. Here it's mostly emission, things like that there. All right, so that gives you a quick look. Now you might figure out what you want to analyze. If you want to get this sort of a thing, you want to pull out the spectrum of a part of the galaxy, you're going to go through the steps I showed near the beginning. Okay. And you're going to plot wavelength versus the flux at whatever coordinates you pick out. Now, like we did with, here we just took a single pixel and we plotted the spectrum from that pixel. But you can do the same thing where you take an entire region and you sum up all of those within it. To do that, you would need to do something like this here. Let me see. Like this here. You would need to use the where function, and you would find the indices, the spatial indices, x and y coordinates, where the x and y, you can just draw a circle around the point that you want and say x squared plus y squared must be less than whatever radius from that point. Or x minus x naught squared plus y minus y naught squared must be less than whatever radius. And then that would give you a circle, and then you would sum it along axis 1 and 2. I'd have to look up how to do that. Anyway, that would add up the spectral information for all of the pixels within that circle. So you'd have index X, comma, index Y, comma, wave, or just colon there. And then that would add that all up. That would take a little bit more work, but you could figure it out from this here. And then you'd be able to find the spectrum of that region alone and not just a single pixel. And what I would recommend would be look to find what the features are in the image first, and then select certain areas along that, certain regions along it, and find their spectra. And then try to find where the spectrum is interesting or different. And a very quick look again is simply by taking the region in DS9 and move it around while you look at the changing spectrum then. That's always my first place to look. Okay. I see.
Thank you, sir. Sir,
all right.
how will we reduce the noise? You told they will be too noisy.
I'm sorry, say that again. If the image is too noisy?
Yeah, how will we moving that, the noise?
How do you handle the noise if it's too noisy? Two things you could do. One is if you simply want to avoid the noisy regions, depending on what the file format is for your data. If you have, let me see here. All right. If you have, oh, here we go. There we go. You will have either an error array in your data cube or inverse variance, as this has here. So you could create a mask where anything that has an error or an inverse variance beyond a certain limit, you'll simply not use that, exclude it, mask it from analysis. But of course, that doesn't fix the problem. It simply avoids using bad data. What you could do if you have noisy data, you can, in Python, just like you can on in DS9, you can go and you can create a smoothing of it. Okay, well, it's already looked very smooth. Now it's even smoother. And what that does is it applies a Gaussian blur over the whole image or a boxcar average. So every pixel will be replaced by the value of all the surrounding pixels averaged together. And there are other various formulas you can use. That would fix spatial noise. And you can do that in Python. You would write your own routine, but maybe somebody has already written this. And you apply it to the whole image and you can smooth that out. On the other hand, you may also have noise along the spectral axis. In that case, you could do the same thing where you average out, you apply a smoothing function along that wavelength axis there. You always lose information when you apply smoothing, but at least you would be able to use the data at lower resolution then. The X-ray astronomers have to do this a lot because, as I see someone else, Vignesh, has written back in about using Chandra data with the X-rays. There are so few X-rays that the statistics are generally very poor, and you need to apply a smoothing function to be able to use them at all. So, but we can do that with visible light images as well. Let's see here. Going back to Vignesh's question about using, the point sources. So I'm working with Chandra X-ray data where I need to remove the point source objects in order to look for emission. Tried with DS9, but I can't remove it. So yes, you would have to do it. You can't do that with DS9, which can give you a very quick analysis, but not very sophisticated. For that, you might have to look into XSpec. I'm going to write this down here. Written by Keith are known at NASA Goddard Space Flight Center. And this is, I don't know if you're familiar with it. If you've been using it for Chandra data for a while, I assume that you know about it. But for the rest of you, XSpec is, I assume that maybe the most widely used X-ray analysis package. It does spectral fitting. I don't know, however, if it does image fitting. And for that, I'm afraid I may not be able to help you. I have done some X-ray training, but I have not really done much analysis in X-rays. My expertise is in optical and infrared. I'm sure that somewhere there is a package or some bit of software that would help you fit point sources to X-ray data. I just don't know what that is. I'm sorry. But check XSpec and see, maybe they have some imaging routines in there as well. And I would expect that even in imaging data for X-rays. I don't remember what, it depends on the camera you're using with Chandra, but it may have energy or wavelength or frequency information as well, in which case you would want to fit the spectrum to the point source as well as the image extent of the point source there. So make sure that you know how many dimensions of data you're having to deal with. Other questions?
Hi. So my question is regarding the sky correction. So
Yes.
when there is no dedicated sky observation, so how do you handle those telluric lines correction for the data using the Python?
Okay. For this, you would want to do, so the telluric, she was asking about sky brightness emission lines. And so these are the Earth atmosphere lines, telluric lines. Assuming that your field of view is reasonably narrow, most of these are going to be, if you're not doing an all sky wide angle kind of an image, then I would expect that the sky emission lines are going to be constant across the field of view, the same everywhere. What I would do would be to go to, pardon me a second, let me take a look. I'm going to stop the smoothing. All right, there we go. Oh, in fact, what I should do is I should go to my, the Muse image. Okay, this is the Muse image. Okay, there. Now, I'm going to create a region here. I'm going to bring it out to the darkest part of it, which is going to be mostly sky. Okay, I double click on it. And I do the plot 3D. Okay, this was a great example here. I'm glad you asked this because I've actually got an example. So as you can see here, when I went to a region that is dominated by the sky, we're seeing these lines here. These are all telluric lines, sky emission there. So as I go through and move around to other regions, you see, now the DS9 will automatically scale the axis for the spectrum to get in the maximum and minimum flux there. If I stay in the sky areas, these look about the same. But if I go into a region dominated by the galaxy, notice that those disappear or mostly go away. They're still down here and they're still at the same level, but it has scaled the vertical axis much differently because now it's trying to fit in all of this and you just can't see them as easily here. They're still there. So what I would do would be, if you have enough region that you can say is definitely sky, you can take the spectrum of that part of the sky and you might even add in another spectrum like over here. Okay, trace that out, take that spectrum and subtract that, and it would be the same intensity, same number of flux per pixel. for every pixel throughout the image and simply subtract that spectrum there from it. That would be the best approach, I think. In fact, although I haven't used this very much, I expect that is another advantage of the integral field units, because if you were doing it with a long slit spectrum, it would be likely that you would only have data from your target, and you might not have sky data, depending on how they do the observations. In that case, then, you would not easily be able to identify the telluric lines. But here, you've got a spectrum everywhere within the field of view, and you can subtract them. But make sure that you know that you get the flux per pixel or per spaxel of an IFU. And so you're subtracting the same intensity per pixel then. Does that answer the question?
I have to take the flux within the beam size, and that spectrum I need to subtract from every pixel, I mean spectral.
I'm sorry, say that again. I didn't quite understand what you were explaining.
Okay.
So we take the sky area here.
Okay.
And we need to find out the size of this region. So we can pull up statistics. Again, you could do this in Python and you'd have more control over it. But if we're doing it with DS9, then I have to look things up. This is very small, I admit, but this will tell me the area in arc seconds or in pixels. Number of pixels is 62, for example, here. And I can look at the intensity here. I can divide it by the area of the region that I'm using, and that should get me a spectrum. I divide the whole spectrum by the area in pixels, and that should get me the intensity of the spectrum for 1 pixel of the sky. We can assume that is the same for every pixel. And so you would write a routine that would go through, and for every, let's say, spatial pixel within the data cube, you subtract this one-dimensional array from it along the wavelength axis. And that should get rid of all of your telluric lines.
Okay, I got my answer. So my second question is why we will be using the Python instead of its pipeline, which is available, like until I reduce the data.
So I'm sorry, you're saying why do we use the Python instead of the pipeline?
Yeah.
What
Till the data reduction, not the analysis part.
Well, in fact, for the manga files, the data analysis does all of this for you. I was using it as an example of how to go through an easy to analyze set of data. But if you go to the manga page, see, this is the tutorial here, and over here somewhere. That's in Marvin. You can analyze it there, but hang on just a second here. In some of these, I wish they made that a little bit easier. Data model. It's going to look for data products. Manga. Well, anyway, on the main, let's see here, back to manga tutorials, about manga, using reduced manga spectra. So anyway, manga actually does do all of this stuff for you. And so it will give you files that have, say, I think like the H alpha image, the O3 image, things like that there. And so this may not be important to you for that one, but the same analysis techniques will work with just about any integral field unit. If you have to go through it by hand, these techniques would work, although the data structure may be different for one telescope versus another one there. But yeah, the manga analysis pipeline is fantastic.
Okay, thank you so much.
You're very welcome.
Come fast. But fast. Tim, because we are already.
Thank you for the presentation, sir.
You're not loud enough.
Thank you for the presentation, sir. So my doubt is we are using here integral field spectrograph, right? But we, for Boss spectrum, if we are taking a galaxy spectrum, they use optical fibers. For in manga, you're using integral field spectrograph. So what additional benefit that we get? Because anyway, we are getting a high resolution spectrum in both of them, right?
So I may have mixed up a little bit, but you're saying comparing to manga, the one that you're using is a fiber-fed spectrograph. Is that correct?
Yes, yes. Like from Boss spectra, like just like the Boss spectra from
Okay.
SDSS, we'll have spectra that we obtain from fiber, like optical fibers, right? So
Yes.
in manga, this is integral field spectrograph.
Right. So are you asking what the differences are between the Boss spectra and the manga spectra then?
Yes, yes, yes.
Okay. I don't actually know. I have not aside from running through this using manga as an example, I have not analyzed manga data myself. So I don't know if they have a greater spectral resolution than Boss or not. But the difference here is that you get the spatial information along with it. Taking a look at it, let me see if I can find the manga overview. There's an image I want. Here we go. This is what I wanted to show you. All right. So for the manga survey, which stands for the massive nearby galaxies, something like that there. All right. So every location where there was a galaxy that they wanted to study with this, they made a new plate and they plugged in that little plug there with this hexagon of fibers. And so again, it is like Boss, it is a fiber-fed spectrograph, except you do get a little bit of spatial information here, where we can see the differences between, say, the center and on that side on there. But in each individual fiber, all you're getting is a spectrum. It's just that you know the location of it better. It is good then to use the manga data along with the Sloan image for that location, because the Sloan imaging camera provides much more spatial information, and you'd be able to identify the spatial features more easily than you can even with the IFU. So here is an example of the Sloan image, and then within the purple hexagon is shown the area covered by the manga integral field unit. So, and with the lady who was just asking the previous question about why would we need to go through these steps instead of using the data analysis pipeline, this shows you examples of what is done with the data analysis pipeline for manga. Here's an H-alpha image. Here's a Doppler shift showing the gas velocity, and the same thing showing stellar velocity using different spectral lines. And then here, using what's called a spectral index, the D4000 is, I believe it looks at the 4,000 angstrom break in a galaxy spectrum, and that's a rough estimate of the age of the stars in the galaxy then. And so here, but anyway, so getting back to yours, Boss gives you a single fiber, and manga gives you 60, whatever, a lot of fibers along the same galaxy. So Boss may only get you the very center of the galaxy, and manga will get you all of the parts out to a certain radius there.
Okay, sir. Thank you.
You're welcome. See, Vignesh is asking for my email. I'll send that out to everybody here in the comments, and feel free to email me.
Okay. Okay. Yeah. Yeah. So thanks so much, Tim.
You're very welcome, Priya. Thank you for inviting me.
I think the rest of the questions will come by email.
Okay. All right. Well, good morning, everybody, and good night for me.
Yeah. Thanks so much, and see you next time. Yeah, next time we do it with SkyFit.
Hope to actually be in person someday then.
Yeah. That should be done. That's right.
Oh, and I will email you the PowerPoint right away then before I go to bed.
Thanks a lot. Yeah.
You're
Thanks
welcome.
a lot.
Good night, everybody.
Thank you so much. Good night. Bye-bye. Okay. Now what I will do, should I leave the meeting? No, I'm 1 minute. I'm a little, okay. Yeah. So now we are going to continue with our session. Here we have Dr. Akshay Rana. Dr. Akshay Rana is our boss in cosmology. We have this mix-up of people basically because obviously everybody doesn't specialize in everything. So Akshay is going to be the one who's going to handle cosmology. There's a big group also here come for cosmology. Akshay teaches at St. Stephen's College in Delhi.